Good day. On behalf of the Joint Industry Project Corrosion Inhibitors, I would like to welcome you all to the webinar series on precision in corrosion inhibitor selection testing for oil and gas applications. Precision, the first right step. In this webinar, we will focus on how in this webinar, we will cover two things. One, what are the objectives of the webinar series? And then we'll talk more about the joint industry project. The webinar series was established to promote broader awareness across the industry on the need for developing standard test methods with published precision for corrosion inhibitor evaluation and selection. And today we are conducting webinar 7. All the 7 webinars focused on the first bullet. Why do we need to develop standard test methods with a known precision? The second objective of the webinar is to explain the process of developing standard test methods. The next 3 webinars, starting from next week, webinar number 8, 9, and 10, will cover this aspect. In fact, we will have presentations from ASTM and probably AMP on how they develop standard test methods. When we say standard test methods, at least in the ASTM terminology, they have to publish what is known as precision. What is the variability if the same person does the test or different persons do the test? As a consequence, the development of standard test methods requires collaboration and coordination. If you are going to develop a standard test method for ASTM, then at least 6 laboratories should conduct a test to produce results, and those results will be compared to develop the precision statement. The third point is the importance of collaboration and coordination. Assume that we have achieved these 3 objectives and we developed the standard test methods. This will have huge impact in our oil and gas industry. And the last 5 webinars will cover how these standard test methods, after they have been developed, will impact the selection of corrosion inhibitors. These 4 are the main objectives of this webinar series. And we'll also cover as to what we are doing in the joint industry project, especially on the development of best practices for evaluating efficacy of corrosion inhibitors that are used in the oil and gas industry. We have seen this one several times. The main drivers or the motivation for the joint industry project, as well as the webinar series, is to take care of, as Trevor Place pointed out, the problem child, which is corrosion inhibitor selection. As you can see, inhibitor selection testing is not regulated, which is a good thing for us. We have flexibility. However, the inhibitor selection at this stage is qualitative. We don't have any quantitative criteria, at least as an industry. We may have some at the company level, but as an industry, we do not have any quantitative criteria. On the other hand, for other corrosion control strategies such as material selection, coating selection, and cathodic protection application, we do have quantitative criteria that are being religiously used consistently across the world. That is a gap we are trying to fix in this JIP as well as in the webinar. Again, I believe we are in the pivotal moment. These standard test methods, they don't get developed within a day or two. It's a long process to develop consensus. For example, to develop consensus on cathodic protection, the industry took almost 20 days.
Hey, Sankara.
The standard test methods don't get developed on their own. The industry worked very hard over a period of 20 to 30 years before a consensus standard was established. For example, to develop the famous NACE RP0169, the industry took almost 25 years. For coatings, the industry took almost 30 years. For materials, it took another 20 years. It's a long process, but for corrosion inhibitors, this was identified as an issue, at least in Canada in 1990s, and we are still working on it. Hopefully, by the end of this JIP, we should be able to have a consensus iconic standards published and being used across the world.
Well, Sankara, good things take time, so there's nothing wrong with that.
That is true, Motion. Thank you. Yes. The point is being consistent. Thank you. Okay. So with that background, let me share with you some of the experiences I had with respect to helping industry to control corrosion using corrosion inhibitors. In the webinar series number 7, we will discuss, will a corrosion inhibitor that works well in one application also perform effectively in other applications? To answer this, I'm going to discuss with you 5 case studies. One, how the inhibitor had impacted the operations in the oil and gas separators. How the presence of oxygen impacted corrosion inhibitor. How an odorizing chemical that was added affected corrosion inhibitor. And how the corrosion inhibitor affected stainless steel tubing. And finally, one case study where the combined effects of corrosion inhibitors, biocides, and scale inhibitors made a huge impact in the particular company. Let us start with case study 1. In this particular case, the operator decided to change the corrosion inhibitor. Again, this inhibitor was injected in a production pipeline. Within 2 weeks after the new inhibitor was injected, the downstream oil and gas separators reported foaming issues. They couldn't separate oil and water because of the formation of foams. The issue was the foaming tendency of the new corrosion inhibitor was not evaluated before it was applied in the production pipeline. When this issue started, the company, at least the separator oil and gas separation unit, tried to apply a defoaming agent to solve this issue, but that did not resolve in the foaming problem. Ultimately, the operator was forced to revert back to the original corrosion inhibitor. Like a magic, after two weeks, the problem resolved. So the lesson learned from this case study is that evaluating the secondary effects of corrosion inhibitors or secondary inhibitor properties, such as foaming tendency, is critical before its implementation. We still don't know why they decided to change the inhibitor, but when they went back to the original inhibitor, the foaming issue was resolved. The second case study, I was given the corrosion coupon data from a production pipeline over a period of 3 years for analysis because of one issue. So when I got the data, what I found was the coupons installed downstream of the facilities exhibited increased corrosion rates. However, coupons installed upstream of the facilities did not show any increase. They were kind of steady over a period of 3 years. In this particular case, the corrosion inhibitors, or rather one inhibitor, was injected into the production pipeline upstream of the facility. And the company assumed that that inhibitor that was applied will remain effective in the pipeline sections located downstream of the facilities. Before my involvement, this has been ongoing for almost 10 years, and they were successful. Both the corrosion data coupon upstream and downstream were consistent. When they saw increased corrosion rate in the downstream facilities, that's when they hired me as a consultant. So what we found was one of the tanks in the facility side was open for some reasons, and they did not put the roof back. As a consequence, oxygen ingressed. The presence of oxygen in the facility rendered the inhibitor ineffective. As a consequence, it was not effective in the downstream, but since the inhibitor was applied upstream, the roof issue in this particular tank did not affect the performance of inhibitor in the upstream section. But in the downstream section, after the tank, because of oxygen ingress, the corrosion inhibitor became ineffective. So the lessons learned were obviously evaluate the effectiveness of corrosion inhibitors in the presence of oxygen. Even though oxygen was not anticipated in this operation, it is always a good idea to be proactive to evaluate the inhibitor performance under various potential conditions, and more importantly, educate the operators on the impact or negative impact of their operations on other performance, such as that of corrosion inhibitors. So in this case, clearly, the inhibitor was good, but because of the operational deficiency, it became ineffective. Case study 3. Again, in a particular wet gas pipeline operation, some sections of the pipelines, some pipelines were seeing progressive increase of black powder formation. Again, this was a series of wet gas pipeline, and they were all protected by corrosion inhibitors. Again, this was the first data I received. As you can see, this pipeline section had several pipes, and not all the pipes experienced increased black powder formation. As you can see, in 2016, 2017, 18 framework, section 1, 2, and 3 exhibited higher black powder formation, whereas section 4, 5, and 6 did not see any increase of black powder. When we dig through, we found that this issue appeared to have started when they introduced odorizing chemical in the upstream. The reason was the upstream section of the pipeline, because of the regulatory change, because of the increase of population, they have to change the zone from populated zone to a populated zone. As a consequence, the company thought it would be a good idea to inject the odorizing chemical so that if there was a leak, that could be detected in the populated area. So they took the precautionary decision. However, what we found was not all pipelines experienced an increase of black powder formation, as you can see from this table, but some pipes distinctly had black powder formation. And we went through the flow pattern of this pipeline, and what we found was the pipelines that were receiving gas streams from upstream that contain odorizing chemical experienced higher levels of black powder formation. If the flow went through the black powder, it went through the odorizing injection port, those flow had increased black powder formation. Pipelines that were receiving gas streams that were not contaminated with the odorizing chemical did not exhibit elevated black powder formation. So clearly, there was an interaction between corrosion inhibitors and the other chemical, in this case, the odorizing chemical, that was introduced at a later stage. So the lessons learned was evaluate the interactions between corrosion inhibitors and any other chemicals that are being introduced. If we do not evaluate, then this will result in some unwanted side effects. So this particular company ultimately decided to stop injecting.
Sankara, just a quick note on this, what you just said. It's not just the compatibility. In this case, it's the loss of corrosion inhibitor or chemicals to the black powder. That's probably what's really affecting the performance of the corrosion. So it's consumed by the by the solids rather than going to the steel pipe. I think that's another aspect, not just compatibility.
Very good point, Motion. Thank you. Yeah, that could be another point. But this had a higher amount of black powder formation. It could be that the inhibitor was reacting with the odorizing chemical. And as you pointed out, it could be that we are losing corrosion inhibitors due to the black powder formation.
To give you just an idea how important that is I think the surface area, if we talk about iron sulfide, one of the iron sulfide pyrite, I think 1 gram of pyrite provides 5 square meter of surface area, if I remember right, or something around there, just to show you how much surface area is available to absorb the corrosion inhibitor. So most of the corrosion inhibitor will go to it rather than to the steel pipe. It's really a very important point to make for this case study.
Thanks, Motion. Really appreciate it. Yeah. Okay. Moving on to case study number 4. In this case, this is a downhole tubular production. Again, coupon corrosion data from production pipelines indicated elevated corrosion rates. And they also experienced failures in their downhole tubulars. When we reviewed this project, we found that the corrosion inhibitor was injected through a stainless steel capillary tubing, which was 6.35 diameter, outer diameter. And when they had this issue, I was involved. And what we found was that they were injecting corrosion inhibitor at a higher concentration that negatively interacted with stainless steel injection tubing, leading to the plugging of the capillary ports. Basically, no inhibitor was being injected into the downhole tubular because the hole was plugged. The interesting point in this case is that because the inhibitor was not being injected, that the inhibitor tank was always full, the operator did not notice that the inhibitor volume in the storage had not reduced for a long period of time. He or she could be thinking that he was saving or she was saving money, but actually the inhibitor was not injected at all because of the plugging of the injection port. So the lessons learned in this case was that evaluate the effectiveness of corrosion inhibitors at the actual concentration at which they are injected through stainless steel capillary tubing. In the particular case, they did evaluate the compatibility of inhibitor with the stainless steel capillary tubing. However, the concentration they tested was not the actual concentration. They had diluted corrosion inhibitor when they did the testing. But in reality, they applied neat chemical through the stainless steel tubing. So this case study also reminded us of the forgotten basics. The corrosion inhibitors rather, which are chemicals, some chemicals, when applied at higher concentrations, can themselves become corrosive. So if you are applying corrosion inhibitor at a particular concentration, you better evaluate, you better do the lab testing at those concentrations. The final case study, actually it was published in the NACE conference few years ago. This was a very extensive study that involved a PhD student from Venezuela spending 2 years in Canada to understand and resolve this issue. In this case, internal corrosion incidents continued to occur despite addition of corrosion inhibitors. The inhibitor package they were using had corrosion inhibitor, biocide, as well as scale inhibitor. Obviously, they had corrosion issues, microbial issues, as well as scale formation. Again, this was not my work, but I was a collaborator, a PhD student from Venezuela, kind of resolved this issue. But before he started, the recommended dosage by the vendor was 30 ppm of corrosion inhibitors, 200 ppm of biocide, 10 ppm of scale inhibitor. This was what the vendor kind of suggested. But in the field, they were adjusting the concentration to range from 5 to 30 of corrosion inhibitor, 20 to 200 of biocide, 1 to 10 of scale inhibitor. So this work was done by Antonio Turis, and he systematically carried out a test. So what he did was first he picked the corrosion inhibitor at 30 ppm, that is the recommended concentration. No biocide, no scale inhibitor. He found that the corrosion rate decreased by 72%. The mass loss decreased by 72% because it's a corrosion inhibitor. However, that particular chemical did not have any impact on the microbes nor on the scale dissolution. He came up with a formula that the corrosion chemical treatment efficiency was only 35% if you just inject corrosion inhibitor from the package. Alternatively, if you just inject the biocide, it had a huge impact on the microbial activity, but not on the corrosion rate, not on the scale formation. According to him, the chemical treatment efficiency was 72%. If you only use scale inhibitor, obviously it did not have any impact on corrosion rate, nor on microbial activity. Obviously, it had a good impact on scale formation, that is scale dissolution. But in terms of chemical treatment efficiency, it was only 48%. Then what he did was he combined corrosion inhibitor and biocide. Obviously, it had a good impact on corrosion rate as well as microbial activity, but less impact on scale formation. Efficiency 72%, 78%. But if you had all chemicals, corrosion inhibitor, biocide, and scale inhibitor at the recommended concentration, that package would have controlled the corrosion rate. But the chemical treatment efficiency was almost 96%. As I said, the package had corrosion inhibitors, biocides, and scale inhibitors. But the ratio chemicals were prescribed by the field operators. Of course, they consulted with chemical inhibitors, but the dosage they used was less than the recommended dosage. In other words, the ratio was not strictly followed, resulting in both microbial activities as well as scale formation that resulted in under-deposit corrosion. This issue was resolved because Antonio systematically went through the various inhibitor package using ASTM G202 with published precision statements. In fact, Antonio came to Canada because he wanted to do the rotating cage. As a consequence, he established the ratio of ingredients to be established. More importantly, quality control in the field so that the prescribed dosage is applied in the field. Again, as I said, this was published in a NACE conference a few years ago. So the lessons learned from all the 5 case studies are that secondary inhibitor properties are critical as efficiency in establishing efficacy of corrosion inhibitors. In terms of secondary inhibitor properties, we have 3 standards: ASTM G170, NACE 31215, as well as NACE 21415. This specifically addresses the influence or negative impact of any chemicals in the refinery operations. In our phase 2 report, the flow chart requires evaluation of secondary inhibitor properties so that the efficacy of corrosion inhibitor application can be ensured. So the lessons learned from webinar 7 is that secondary inhibitor properties are vital. With that, let me go through once again the focus of the joint industry project, especially the phase 3. As explained earlier, the joint industry project has got 3 objectives. We are in phase 3. In phase 1, we collected and summarized existing best practices from owner operators as well as chemical developer and suppliers. And we did 226 interviews. However, just wanted to point out that the 5 case studies I discussed today were not part of these 226 interviews. And anything that was collected for the phase 2, for phase 1, will remain confidential with the sponsors. In any event, based on the information from phase 1, we developed guidelines representing the industry best practices for corrosion inhibitor testing. We wrote 23 individual reports covering each one of the applications. Based on phase 1 and phase 2, we identified 8 lab methodologies that needs to be standardized. That is the focus of phase 3. Again, in phase 3, we will develop precision based on repeatability. That is, what is the variation if one laboratory conducts a test. This phase was officially launched on December 2nd, 2025. Again, I would like to thank all the sponsors. Right now, we have got 11 sponsors, but we also got feedback that 3 more sponsors are going to join the JAP shortly. So in this particular webinar, I would like to focus on why we want to develop a benchtop rotating impeller test for inhibitor efficiency evaluation. Again, in total, the plan is to develop standard test methods for all the 8 methodologies that were identified here. So let us focus on the benchtop rotating impeller test. That is to evaluate inhibitor efficiency. We simulate flow in the laboratory so that the impact of flow can be simulated in the lab. And there are 2 schools of thoughts. In one side of the thought process, when you simulate the flow in the laboratory, the specimen is also in motion. Classic example is rotating cage. When you use rotating cage, both the specimen in the cage as well as the flow or the solution are in motion. So the specimen also moves around. Same case with rotating cylinder electrode, where the specimen is a cylinder which also rotates. It's in motion. Same thing with rotating cylinder without the electrode. It also rotates. The specimen also rotates. And the rotating probe, which we do not use, but in that methodology also, the probe moves. In other words, in this set of laboratory methodologies, when we simulate the flow, the specimen is also moving. And this is well recognized, and people are comfortable using it, including me. But there are some few people who think that we have to simulate the flow in the laboratory. However, the specimen should be stationary. That will better simulate the field operating conditions. And that is their school of thought, which is also appropriate. For example, if you do the field testing, we insert the coupon, the flow happens, but the coupon is stationary. If you do the lab testing, there also we insert the coupon is stationary, but the flow happens along the flow loop. There are 2 other methodologies in which the coupons are stationary. For example, if you take jet impeachment, again, there are 3 versions of jet impeachment as per ASTM G208. The one from Canvet, it has got 4 arms in which the coupons are stationary. The jet impinges onto the coupon. but the coupon is stationary. And one particular company is very keen on having the coupon stationary, and they use the impeller. So in our JAP, we are going to standardize the benchtop rotating impeller test, in which the coupons are stationary, but the flow is simulated by the impeller. So that way, we kind of satisfy both schools of thought. For those who are comfortable in using specimens that are in motion, they can use this set of experiments. Especially, we will be standardizing rotating cage and rotating cylinder electrode, 1 liter, 1 liter. For those who want to specifically use flow simulation with stationary coupon, for which the benchtop rotating impeller test will be valuable. That is the reason why I picked up the rotating impeller test as one of the methodologies for standardization. Again, I would like to thank both SET Laboratories and Canvet for sharing the photos that are used here. So in summary, in phase 3, we will develop step-by-step procedures to carry out a test for all methodologies that will be standardized. For those new methodologies that are being developed, we will develop the blueprint. And these blueprints will be given to the sponsors that will enable the sponsors to manufacture their own apparatus. As a part of standardization, we will also standardize solution compositions. We have established 5 standard solutions that need to be standardized. These solution composition standardization will also include procedures to prepare them, both in terms of solution as well as gas saturation. We will establish the precision based on repeatability. That will be the end of phase 3. At the end of phase 3, after the sponsors approve it, we will either submit to ASTM or AMP. We are thinking of ASTM because ASTM can publish standard test method based on repeatability. And we will work with ASTM to continue on developing reproducibility statement that requires round-robin testing or inter-laboratory studies, based on which we can establish reproducibility. So that's all we have for today. I really appreciate the discussion.